guy, the operating system can be run at 1. And we went over the problems with doing this, is that typically operating systems run in ring 0, now it is running at ring 1. Not only does it know that it is running at a different level, but there are some instructions, especially the x86 instructions, that do not behave correctly when it is 1. What you want to is, you want to basically have every instruction that touches hardware to trap, like any system call, to trap into the hypervisor. Unfortunately, there are some instructions that do not do that. So therefore, it will result in wrong behavior, and we figured out how to do trap and emulate and so on. But today, what I want to go over is a little bit more detail in this whole, as I told you recently, both Intel and AMD, they have provide hardware support for virtualization. Okay. What does that mean? So if you look at the both AMD and all the modern day processors which support virtualization, they have two modes: virtual machine mode and the root mode, or the non-VM mode. Okay. Now, here in this also you have 4 rings: 3, 2, 1, and 0. This you don't have to worry. This you don't have to worry. Similarly, we have here also we have 4 rings in each. 2 and 1 are not used, so we don't have to worry. Only thing is here, this mode 0 is not really mode 0, in the sense that when I run a piece of, this is my memory, when I run a piece of code in this mode, if the CPU is in VMX mode, ring 0, okay, if the CPL level, okay, is that VMX mode is 1 or VMX mode is 1, and this ring 0 is quite different from if the CPL register is 0, 0. Okay? This is the non-root mode. So the privileges of this guy is that if the CPU is running some instruction that belongs to whatever it is, if it's executing some instructions and the CPL is 1, 0, whenever you execute in and out any hardware, like changing the page table register, the interrupt vector, etc., these instructions can be configured to trap into code that belongs to 0, 0. This is the root mode, and this is the CPL. So this is most modern processors which support virtualization. Basically does that. So whenever an interrupt occurs, I can configure such a way that the hardware will jump into some area of memory and the CPL will change to 0, 0. Okay? Root mode, and then the current CPL is 0. Okay? So this guy, now the hypervisor, okay, can do whatever it wants because it is the highest privileged level. It's in the non-root mode, root mode, and also at level 0. So this can manipulate hardware and so on and so forth. And the idea here is that, see, now we'll get rid of this problem of worrying about instructions that don't behave correctly, because the guest operating system or the VM can be configured to run in this quote-unquote VMX mode, ring 0. Now, anytime I execute any privilege instruction, I can configure it to trap into the system. Okay? And not only that, as far as the OS is concerned, it thinks or it continues to run in ring 0, so it doesn't know that it is running as though nothing had happened. It's running in ring 0, and the hardware is set such a way that when any of these instructions are executed in ring 0, I will trap, and the trap goes to the hypervisor. Hypervisor will do the stuff and get back. Okay? So now, the one example of this hardware supported and virtual machine that uses, nowadays almost everybody uses this hardware. First one is the KVM of Linux. Okay. So what does it mean? Right? Remember, we have literally 4 modes, actually 8 modes, but for the time being we'll only look at okay. This is the VMX mode, this is the root mode. For all you know, all you have to know is this 0 is more powerful than this 0. That's it. So, how does KVM Linux manipulate or make use of system virtualization? So, assume this is a user level process, like any other user level process, running on a host operating system or hypervisor. You can call it VMM or hypervisor. And that is in root mode, privilege level 0. This code is always running at root mode and privilege level 0. Now there is a user level process called QEMU. Stands for quick emulation, okay, which is responsible for loading up the different virtual machines. Okay. Now, remember, for the time being, let's assume a virtual machine is nothing but a copy of some version of OS. Linux 1, Linux 2, Linux 3, whatever. So this guy is like a manager, user level process. He needs to boot up some virtual machine or some operating system somewhere, and then it has to reside in memory. And this process I could create multi-threaded, etc. But for the time being, assume this is one process. I need to basically launch a VM. What does it mean? I need to make sure that I need to copy the code of that operating system or that virtual machine somewhere in memory. Okay. And then ask this guy to start executing that piece of the code in this mode. In VMX mode, 0. Okay. So what does it mean? So what it does is, first of all, remember this is a process. It needs to ask the hypervisor in the root mode to say, give me some sufficient memory so that I can boot my operating system or virtual machine. Okay. So the best thing is I will memory map some OS that is there in some file system. VM. So whenever this is a user level process right now, running in root mode. For all you know, it's just acting as a normal process. And then, what does it mean? Memory map meaning all the code that belongs to this operating system will reside somewhere in memory. Right now, I memory mapped it to KEMU. This basically nothing but your guest operating system. Now, all these calls, okay, remember these are all hardware supported virtualization. There's a lot more support for virtualization. So what I could do is, I can do boot, but somehow I need to now transfer control of my CPU to start executing this guy in a different mode. So therefore there are some special operations, right? Like something called KVM launch, KVM resume, KVM suspend, exit, etc. There are some operations. And these operations you can assume is like any input-output devices. KVM 0, and then you can give all the operations. KVM launch, etc. So there will be one main thread that will directly interact with the VM, and every VM, with the hypervisor, and every time I create one, I can either create one thread for each of the guest VMs, or I can create a different process. That depends upon the implementation. So now let me take, without confusing you too much, let's for the time being assume I want to only implement one VM running on hardware. You can extend it to multiple VMs as well. Okay? So now what I have to do, find your memory mapped boot of the OS, or just the boot block memory map, and once you start running it, it will boot the remaining code, etc. That's not the issue, but here is the basic idea. Okay? Now I have basically the image of my VM is now resident in memory. Now what I have to do, I have to ask that guy to start executing in that mode. Okay? So now this basically I will do KVM launch. I'll ask the hypervisor to do a KVM launch, which will basically nothing but the process control or the EIP should point to somewhere, and the CPL should go to 00. What did I say? 10. VMX mode, bring 0. Now, so far so good. I have launched it. Launched it meaning the code belongs to the operating system, starts running. It is in this mode now. Now this is a guest OS, so it can create its init process, and then this guy can force other processes, etc. All these processes will run in absolutely no difference. Once you have launched the operating system, it creates its own user level processes, all that stuff.
Wouldn't this be like kind of slow? It has.
Sorry?
Wouldn't this be kind of slow because it has to all go through KVM?
Where is it going through KVM now? No, only the initial launch, right? In the initial launch, somebody has to boot the OS onto memory, right? Earlier the user or somebody, or it would already be as part of the boot process. But now as part of the boot process, only this guy will be in memory. Because it's hypervisor, he is the super user, quote unquote super operating system, right? So hypervisor is in 0 in root mode, and you launch your user level KMO process, and then whatever user interface or command line language, you can ask it to boot different VMs. When the VM is running, right, it is just running in a different privilege level, that's all, right? This is running at 10. Right? This is the hardware support. So you don't, whenever you do the CPL level, you only get 0 for this operating system. It doesn't even know that there is something called 10. Right? This is only done at the hardware level. Hardware knows that it's 10. Okay? Now, if there is no IO instruction, no interrupt, nothing, you won't know the difference. It's happily running, creating processes, fork, exit, whatever, keep on doing this, no intervention. Okay? Normal. Okay? Now, for some reason, whatever, right? Two things can happen. An interrupt can occur, right? That means it has to be handled by this guy, that's number one. Or I can do some privilege operation. This OS can execute some privilege operation, which could be IO, which could be changing the interrupt descriptor table, page table, whatever. Some privilege operations. Right. So now, whatever reason, right, I have already configured that, hey, whenever you in 1.0 mode, when you get to, whenever you execute a privilege operation, you do an exit back to I need to somehow go back to this particular. So remember, when I make a system call, correct? Automatically in hardware, I will store this in kernel stack, and I remember where I was, and then I do an I return, I go back, etc. Now, I have to do something different. It's not just that the OS is remembering where I was in the user space. Now the VMM, or the KVM rather, needs to remember where in VMM I was, or where in which virtual machine I was, handle whatever has to be handled, and then go back to that place. Okay? Keep that in mind. So that means whenever I switch here, I am now going to execute code that belongs to KVM in this mode. Okay. Remember, KVM is also resident somewhere in memory. Only now, what is the difference between when I executed a system call, there was only a mode change. Okay? I was still executing in the same context as the currently executing process. Now, this is a completely different process. This is a different mode, different registers, set of registers, different, code base itself is different. I may be doing something completely different. I may switch to some other VM, etc., etc. So this is not just mode switch. Yes, there is mode switch, but also there is a context switch. I also have to switch the context. I have to remember all these, what were the registers, what were the EIP, etc., etc., and then start executing code that belongs to the KVM. So that means there is a context switch between the guest OS. So from the guest OS, so on a VM exit, so I've configured in such a way that whenever you execute a privilege instruction or an interrupt occurs, there is a VM exit. VM exit switches from guest operating system to host operating system or the hypervisor. While you do a context switch, you also obviously do a mode switch. You go from KVM mode, VMI mode to root mode. Okay. Whatever it is, right? Now, remember, still, I would not know what to do. I would still handle it back. Whatever was the instruction, input output instruction, etc., etc. Okay, and this K move initially has launched that particular operating system, what does it have to do? Let's say, I'll keep that for a while. Some input output instruction. I made a system call. Okay. So normally what would I have done? If this was, let's say, read one block from some file. Some block in the disk somewhere. Okay. So in normal circumstances, what would you have done? So this is system call, you go into kernel mode. Kernel mode has a mechanism to look at the driver, give whatever the operations to read a block of disk. It would be non-blocking, blocking doesn't really matter, but you would directly interact. This would give some command, read command to some device number 0, number of blocks to read, etc. etc. For the time being, don't worry about asynchronous, because once it completes, I'll come to that in a moment. For the time being, let's assume it's a synchronous call, right? Let's not worry about asynchronous. I'll come to that in a moment. It's not a big same thing. So I would have given a read call to some device number, wait until the read completes. I'll get the blocks back somewhere, and then I will tell the user process. I return from this system call. I basically tell where in memory, or give a pointer in memory where the blocks are. And this would have been the normal operation. Now, this is synchronous. You could do that. If it is asynchronous, then you'll have to wait for that interrupt. You will know which device interrupted, what was the corresponding request. So you will know which process had made that request, etc. All right. Now, this is not possible, correct? We don't want guest VM to directly access hardware because it's a privileged instruction. So now, what I will do, make a system call. Instead of directly accessing the device, who should access the device? As far as the KVM should be the one who accessing the device. So therefore, what I will do is, this is a privileged instruction. I will give a KVM exit. To this guy saying this was the instruction I want to do. And then I'll tell the KMU, hey, there was this guy that I need to do. And this guy will initiate the corresponding I/O operation on that particular device. Because remember, KMU is the guy who launched all these VMs. He knows which VM is what, etc. So I know which VM was running. I will go back to this guy. Now, remember, this is root mode. This is root mode 0. So what I will do is, this guy will launch a thread and execute that I/O operation on this guest VM behind. So this, nothing but, so this thread, right, I could block, I could asynchronous, synchronously wait, whatever, doesn't really matter. For the time being, as I said, let's take care of synchronous I/O for the time being. Asynchronous, I'll handle it later. So that means this thread now will issue an I/O operation as though the user level would have done a system call to the kernel. So now this guy will issue a system call to do this, but this guy is perfectly capable of accessing the device. So he will take over and access the device to read whatever has to be read. As far as I am concerned, this is a user level process for me. So let's assume it's a synchronous call. I'll wait for this disk to read the disk blocks. Tell this KMU, hey, the disk blocks are written, right? It's completed. Now KMU's this IO thread returns. Now what does KMU have to do? I have to basically resume the VM, right? So once the IO is completed, I will issue a KVM resume. Okay. Because now you see here, this when I said here, I'm writing the block so that it's basically in some piece of memory that belongs to that particular thing. Because I know the range of memory addresses for which that VM has been mapped. Okay. So therefore, now I will issue KVM resume. Okay. So these are all different, there is something called enter KVM launch, yeah. So this is resume, meaning you want to resume a VM that was already launched and was blocked. There is also KVM launch. A lot of such system calls between the KMU and the KVM. Understood so far? There are a lot of details, but conceptually, this is what's happening. And one good thing about it is, okay, now, okay, this was synchronous, right? Asynchronous is also not a bad. So what you could do is, let's say this was an asynchronous call. That means the IO will not return and you wanted to start something else. What would I do, right? This is all context switch, correct? Here, now this thread is blocked. You initiate another thread and then just do VM exit and let this guy launch, go back to that. So in other words, even before the IO completes, you could do VM resume and he will start executing it. He would have blocked that thread, and eventually when the thread completes, again, go back to this. So there are lots of details, but the basic idea is how hardware supported virtualization works. So only thing now is that I told you that it is more context switch also, so I need to remember all that. Okay. Suspend. I'll resume. So this is some guest VM. I will suspend operation whenever I do a privileged, whenever I execute a privileged operation. I suspend myself and then resume the KVM of the host OS. And similarly, whenever I launch or resume a VM, I basically suspend myself and then resume. And now whenever you are suspending yourself, resuming this, I will need to do a context switch. Because I need to remember all these registers and then go back. Also remember, when I suspend myself, there is no guarantee that I'll go back to the same guest VM. I could be executing code belong to some other guest VM also, but there are multiple VMs in memory potential, right? So therefore, I need to remember all the, just like a process control block, I need to have all this. So therefore, there is a special data structure called virtualized memory context switch data structure or VMCD context block. Okay? That data structure holds all the information that you will need, all the registers, the program counter, stack pointer, all open files, whatever, etc. All that information is stored in some data structure. And similarly, everything about the host operating system is also there. So whenever I am running one guest VM, I suspend myself. When I resume, I reinstate all the state of this guy. Similarly, when I suspend, I store my data, all the current context here, and use this to resume that particular process. Okay. All right. Now, that is when, what about completely interrupt? Even though I'm showing as though it's like this, they're all resident in memory, by the way. Everybody is resident in the same piece of memory. This is my KMU. This is ring 0, ring 3, ring 3, this is ring 0, 3, ring 0. So that is when the guest OS makes a privilege call, I trap into VM, etc. Okay. What about interrupt? Same thing, no big deal. Interrupt occurs, right? Now, remember, every guest OS also has its own interrupt descriptor table, and it has its own interrupt servicing routine. Everybody has its own interrupt descriptor table whenever there's an interrupt. But there are some interrupts that occur only for AVM, for example. Okay. I'll come to that in a moment. There are some that will occur for both, right? What about timer interrupt? Correct? When a timer interrupt occurs, definitely any interrupt this guy will handle, but he should also make sure that the timer interrupt also is given to all the guest operating system, because they're also running their own scheduling algorithms for processes and so on and so forth. Okay? Keep that in mind. We'll see how that is delivered. But for the time being, let's assume there's an interrupt, whatever it is, disk interrupt, keyboard interrupt, whatever happens. I'll automatically come to level 0. The processor status will change to 0 in root mode. Okay. I will have the interrupt descriptor table. So when an interrupt occurs, now forget about VM. In a normal situation, with my operating system with a different processing, right? And there is a timer interrupt, it goes to the OS. OS will do some routine, maybe schedule a different process, whatever. What if it's an IO interrupt? What do I have to do? What happens? Let's say there's an IO interrupt, a disk interrupts. To the obviously interrupt, you go into the interrupt descriptor table, right? So I know which device it is, so there is a corresponding interrupt service routine for the device. Fair enough. after executing the interrupt service routine, what will happen? What should happen? Just normal operating system, we have gone over all the details of this. When, as part of the ISR, let's say this is IO, some disk, I have read a disk block. What, in addition to handling, writing the disk, contents of the disk block to someplace in buffer somewhere, in wherever the memory is, what else I have to do? What else does the OS have to do?
Set process to be ready.
Huh?
Set the first one process to be ready.
Correct. So that means, right, for the process wait queues, right, there will be one different devices, there will be a lot of these processes on the device wait queue. Right? Process for executing, you execute an IO instruction, I put them into the wait queue, and now this is completed. Somebody has completed. So now I have to identify the process whose request is completed and move that guy from P1 to ready state. Correct? So that means as part of the interrupt, I somehow have to identify which process request has completed. That is easy to do that because what I will have is on a per process basis, I will have some notion that where you have to write your status, right? Whatever it is, I will say, look, when you complete, put your status in location 1. Location 2 will be for process ID equals 413, PID equals 415, etc. So I exactly know when the interrupt returns, which process request has just completed as part of the ISR routine. So then I will just go to that queue, push that guy back. Got it? Right? So that's how the OS has done. Now same thing here. Now the KVM has to, when the device interrupt returns, correct? I need to know which VM I need to return to. Correct? So I would know, right? Just like when I gave that request, it came to KVM. KVM would know that which VM returned, right? Or I mean which VM context that particular request was given. So I'll go back to that guest OS and say, hey, this request that came within your context is ready, whatever. And let him figure out which process request that was. Okay? So therefore, what will happen is on an interrupt, right? The interrupt service routine is part of this KVM code, but not all of it because different OSs will have different ways to do that. All I will do is, once IO returns, whatever is the status register and the stuff, I will make sure that it is by DMA, whatever it is, I'll make sure that it is activated. And then based on which VM it was referring to, I will basically now make sure all the data structure and I'll start resuming that particular. So, but basically, each guest operating system also has its own interrupt device table, except that the actual interrupt is handled by the KVM in that sense that it is received by in this mode. I will manipulate, like trap and emulate. I will, as though I handled it, make sure that everything is written in wherever the DMA is, and then resume that particular request. So there are a lot of, what should I say, details on how the hardware virtualization works. If I want, I can do an entire course on system virtualization, but this is just one part of OS. So I'm just going to give you good read up on there are a lot of material online on system virtualization with the hardware support. You can look up that. All right. What about scheduling different VMs itself? Okay. That exactly runs like any other process. Every time there is a particular timer interrupt, the KVM can basically suspend, resume another guy, and so on. Okay. So these are nothing but, as far as KVM is concerned, right? You can do round robin, you can do any of the other standard thing. Basically what you do is you ask it to run for whatever k units of time, and after that again another timer interrupt, you suspend, resume, suspend, resume, suspend, resume. So these are all the different guest operating system. Hopefully you give each guest operating system reasonable amount of time so that it can execute all the other processes also. So basically, you just have to do suspend, resume, and we know how to do that. Okay. So every time a timer interrupt occurs, you suspend this guy, and then resume this guy, suspend this guy. That's pretty straightforward. There's not much very sophisticated, simple round robin with sufficient time quantum. So basically remember, typically the 100 millisecond per process, maybe now you may want to give 1 second per guest operating system, and within that you can give 100 milliseconds to each one of these processes. And of course, if you have multiple CPUs, you can schedule different, yeah.
Apart from timer interrupt, when does this KVM deschedules an entire operating system, host operating system, guest operating system?
When it's, let's say, you mean the IO request, you mean?
Any case apart from this timer interrupt, when can this KVM deschedule this guest operating system?
Whenever, for whatever reason, the guest operating system, if it wants to suspend itself, then it will schedule another OS, right? For whatever reason, you know, some halt instruction, there may be some other instruction that it doesn't want to, then it can. But you're right, very rarely the guest operating system want to suspend itself, right? Because remember, as far as it is concerned, it has access to all of the hardware, it is running all the time. It doesn't know the system, it doesn't know that the fact the system has been virtualized. So if the guest OS thinks it's running happily, whatever it wants, but it just multiplex for timer interrupts, unless there is some explicit system exit or something like that. Okay. Also, for a time being, right, the entire OS will be suspended for a very short time, in the sense that, remember, whenever there is a privilege instruction call, right, that's as good as suspending the entire OS, going to KVM, doing whatever it has to do, and returning back to this particular. Okay. Only on a timer interrupt, you may not only switch from this guy to this guy and switch to somebody else. Otherwise, for a brief amount of time, this will be suspended, meaning there is a context switch. Okay. This code belongs into this guy is not going to be run. Code belongs to KVM will be run. Maybe KMU will be run, and then KMU will give me an IO request, and then I will resume this particular. So there are a lot of situations where, let me put it this way. Under normal circumstances, entire VM is suspended whenever there is a privilege operation. What does suspend mean? Code belongs to the guest OS is no longer being executed. Right? So the code that belongs to KVM is going to be executed. In that, meanwhile, this is quote unquote context switched out. Okay? But the ready queue and all that is very, very, what should I say, as not sophisticated as for this guy, because you are not talking of hundreds of processes. You're talking of few VMs running on one hard piece of hardware. Very rarely you will have 10 or 20 VMs running on the same machine. Containers are different, but VMs very few and far between. But even then, right, I suspend, meaning code belongs to the guest OS, no longer executed. I've now switched mode, switched context to the KVM. KVM goes to KMU saying, hey, there was this IO interrupt, right? So this guy will give me an IO request, right? And if this thread is suspended, this is a non-asynchronous IO, then I can block this thread and create another thread and execute VM resume. Okay. So now that guy will start executing. Right? So the I/O will happen at its own sweet time, and I/O completes. Same thing here, there's another I/O completion is also an interrupt. Wherever I was, I'll go back to KVM. I know this is a return from call. Wherever the DMA was, I'll give the status information back to the OS. And it will start running. Okay. So the way to think about it is that typically I will suspend, resume between guest and KVM, guest and KVM. On a timer interrupt, not only will I suspend this guy, but I may resume a completely different view. That's the only difference. Okay. And then you have to do all this, etc., etc. Okay. Now, let's look at memory management. Alright, so memory virtualization. Okay, so in a single operating system, non-virtualized world, I have different user processes, and I basically convert virtual address to physical address using a page table. And each process has its own page table. So for every range of virtual addresses, I have my own physical page table, and now different processes are mapped in different area of physical memory. And I will need to translate every time a CPU emits a virtual address. I look at the page table. How do I know the starting phrase address? Suppose CR3 has that pointer to that particular starting address, the page table that's in memory. I access that memory, bring the starting address of the page, add the offset, etc., etc. Of course, you don't want to do it all the time, so therefore there will be a what? TLP has a mapping so that you can cache. That is where we were. But now, okay, each guest operating system, right? So this is your normal, but the view is same, it just shifted one level indirectly, right? So each guest operating system thinks that it has all of physical memory to itself. And whatever it, okay. But now we have different virtual machines running on the same piece of hardware. And each operating system thinks it has access to all of its RAM. And not only that, every operating system thinks it is in the highest order of physical RAM, whatever, 4 gig, 2 gig, whatever that is. Right? But in reality, in a virtualized environment, you have different operating systems running. So even though it thinks it has all of its physical memory, the physical memory itself is partitioned among different operating systems.
Is this like statically partitioned or dynamic?
It could be statically partitioned in the sense every OS needs some amount of space to load itself, right? So that much is given, and then plus some amount is given, and then demand paging is used. There's some overhead with that, but I'll come to that in a minute. So that means there is a guest virtual address. Earlier, what we do is you have a guest virtual address, you will take a page table and you will get the host physical address. But now, because the memory itself is partitioned among different OS, I will need another translation. This host physical address is quite different from guest physical address. And the page table for each process, and this page table gives me the guest virtual address, guest physical address. Okay. But this page is somewhere else in physical memory. Earlier, if I knew the starting address of this page, that would be the corresponding starting address of the page in physical memory. I had the offset I would get. But now, even though let's say this is virtual address 0, physical page number 2, but this physical page number 2 could be actual page number 4 in the host physical memory.
Would the memory of the guest OS in the host physical memory, would that be contiguous?
Yes. Yeah. That's an allocation. Remember, you guys studied super pages. Mostly OS if super pages support it there, I can give it one super page. Because that's resident, you need about 2 gig for operating system, just let him be there. Yeah? So that's just a policy decision. Either way, yes, you have to have resident. So that means, right, this is physical page 2, but that's mapped to host physical. So that means I will need another table for each operating system to map the guest physical address to host physical address. Okay. So that means I need to go from guest virtual address to host physical address using 2 different page tables. Okay. So now, remember, the TLB and the main memory management unit, what does it need? What does the MMU need? What is the input to the main memory management in the traditional sense? What will I input? What is the output? I'll give the virtual address, out will come the physical address. Whether you have a TLB inside or not doesn't matter, but this is the actual address bus that goes to the RAM. Right? So that means this guy needs a mapping directly between guest virtual address to host physical address in MMU. So now, remember, this is fine, right? I want to allocate a page, everybody thinks I have 0 to 2M. By normal allocation, each operating system for each virtual address will give it some physical page, some 0 to whatever maximum. Everybody will give the same. So this guest OS may also have some page table, page name or whatever, page 2. It thinks it also has 4, sorry, this also is 2. Right? But this 2, for him maybe 6 or something like that. So that means I need to keep a mapping for each guest. For each guest OS, I need to keep a mapping which combines the guest physical address with this. Now this, who knows for which guest, what is the corresponding physical page is known only by the hypervisor or the VMM. So this table is known by the VMM. For each guest, I'll maintain one table that maps guest physical address to host physical address. And this one is individually mapped by the VM. So now, but the MMU needs a direct conversion between this and this. So I have to construct what is called a shadow table. That combines for the currently executing VM, right? I need to construct this shadow page table, and this is what I will give it to the MM. Okay? So that means for every VM that is running, the hypervisor will construct what is called a shadow page table, which is derived from, this is for guest OS 1, guest OS 2, etc. For each one of them, I will construct one shadow page table. Which will tell me that, hey, this guest OS 2, physical page number 2 is mapped to this host physical address, and this guy's 2 is mapped to 7.4.
So the shadow page table consists of mapping between guest virtual address and the guest
Host physical address.
host physical. So the guest physical address is not maintained. Guest physical address to host physical address.
The guest virtual address to guest physical address is given by the page table of each of the processes in that particular operating system. So I only need to know, remember, everybody thinks I need 0 to 2K, correct? Whatever is the number of bits of the, everybody thinks whatever is the amount of memory I have, 0 to 2K. So whenever I allocate, let's say this guy says, I need to allocate some page to virtual page number 2 for this process, correct? So at that time of allocation, it can, remember it is allocating. I'll come to that in a moment. So let's say it allocates page number 4, right? Fine. But it will not get the actual physical page number 4, it would have gotten in a regular OS. What will happen? What should happen?
It should convert guest physical to host.
Yeah, but anyway, so basically let's assume you want to allocate some page to virtual page number 2, right? Or virtual page number 0, you want to allocate a page. Right now it's not valid, you'll get a page fault. That page fault is a privilege instruction, it will be handled by the VM. So the VM will make this entry into 4 and try to allocate that page. The VMM will basically translate that 2 to 4 here. Okay? So now, all I have to do is to basically, I have to know, remember, this guy each maintains a page table per process. So this is already GPA to GPA. And I know for each GPA what is the corresponding GPA to HPA. But the shadow page table should be for each virtual address directly to that, and that is what should be given. Okay? And remember, at every time you context switch, I'll have to map another corresponding table, right? So therefore, the shadow table will directly give you the virtual address to the host physical address, and that has to be constructed either on demand or could have as many as you want. Because remember, this has been constructed on a per process basis, right? Currently executing, for the currently executing process, I need to know what is the conversion between GPA to HPA. That means there will be that many shadow page tables per process multiplied by the number of guest VMs. That's a lot of shadow page tables running around. But we'll figure it out. That's an optimization, how to get rid of the garbage and stuff like that. So for the time being, assume that the VMM maintains a shadow page table which is constantly constructed between what the guest operating system allocates and what the VMM allocates the corresponding physical page. Okay? So this is a very important structure now. Yeah.
So where does that number 4 then exactly come from?
Meaning, which physical page to allocate to?
Yes, for the guest OS perspective.
Alright, so let's go over this example. say you fork a process. Let's assume another unit process is already there. You fork a process, you create a page table for it. Okay. Now remember, you have a free list. Every operating system has a free list, allocated list, etc. So every OS thinks it has 0 to 2, whatever, 2 power 2 bits, right? So let's say I have something from the free list. The process makes a reference to virtual address 0. Right now, the valid bit is 0, present bit is also 0. Right? I only created a page table, you want a 4. The very first instruction that you will execute, right? You will want to create a page, allocate a page from your free list that you will say this is 4. Right? But this is not really 4, right? First of all, I shouldn't even be allowed to touch it. I'll come to that in a moment. So let's assume I do this, but this is useless. This 4 may not be real 4, correct? So that means every time this operating system touches the page table, right? Who should be notified?
Yeah.
The VM. So what happens is that these page tables, at least in the VM case, will be made read-only. So whenever you try to allocate a page and try to modify this entry, you will get a trap. Okay? Now, when you get a trap, you're saying, hey, I'm trying to what is the reason for the trap? Modify page table entry to make this valid, whatever, 4. Because the allocation of physical, guest physical pages should be left to the individual operating system. That we should muck around. So he's trying to say, hey, I want to put this, I don't care how he got 4 from his free list, right? His free list says, hey, 4 is available for allocating to virtual page number 0. I try to update this, I get a page fault, so to speak, right? I get a trap because all these page table entries in the virtualized mode will be set to read only. You get a trap, okay? Now, I will update my shadow page table saying that virtual page number 0, right? Now, he is allocated 4, I won't touch him, but his 4 is now my host physical address of 6. Right? So now he thinks it is still 4. I will return from the trap and make this 1 maybe present, I'll make it 4. I won't touch it. I have done this modification, not the guest operating system. So the hypervisor has made that, created this shadow page table for that particular process, and now whatever I call it, guest OS 1, P1, whatever. Okay. So now this from host guest virtual address to host physical address is my shadow page table. And that can be in the TLB, and that is what I give it to the MMU. Okay. And this will be, CR3 will point to this shadow page table. Okay. Now when there is a context switch or when a new process executes, same thing happens. Okay. So I have a new thing, what happens? Again, what will happen now? So let's say this is fine. Now there's a context switch, I go to a new process. As soon as you go to a new process, what do you have to do?
Shadow page table is closed.
Not yet, you don't know. I'm talking about this guest OS. Let's say this guest OS is running. On top of it, P1 is running. Now P1, you move to P2. Under normal circumstances, what would happen?
This page is
Saves the page table.
Page table changes, correct? What does it mean to page table change? What has to happen?
Censorship.
right.
You save it from memory and then take the new one.
Don't worry about saving. Let's assume I have enough memory. But what does it mean to go to a new page table?
Change the address of the CR3.
Huh?
Change the CR3 pointing to.
Now CR3 has to point to a different page table. But modifying CR3 is a privileged instruction. Right. Okay. So touching CR3, reading CR3 is okay, but changing CR3 is again a privileged instruction. I get it to VML. I now know which shadow page table I have to. But remember, this is a lot of data structure. Okay, lot of shadow page tables will be there in the VMM space. Okay? Yes, it's not big, but still, that's a lot of memory that I have to accommodate, right? But think about it. As I said, don't remember each operating system can hundreds of processes, but we are not talking of hundreds of VMs. That's too heavy weight. Okay? Typically, you will have 2 or 3 VMs running on one. Don't confuse with container, but that's why containers came into play, because this is too heavy weight. Running hundreds of guest operating system on a piece of hardware, it will be very slow. It's not worth it, it's not needed. Maybe 2 or 3 guest operating systems on one piece of hardware is reasonable. Okay? So now your overhead is nothing but number of guest OSs cross number of page table you have. Okay? Now, one naive assumption is I will keep all the shadow page tables for all currently running processes. Remember, when the process terminates, I release the page table, I can get rid of my shadow page table. But at least conceptually, I'll have to retain number of guest OSs cross number of active processes. That is my data structure overhead. Correct? But what if I say, hey, I can only afford shadow page table for K of them? You can get rid of them. Next time on demand, when you try, you rebuild. Not a big deal. Okay? So that's just a policy decision. Okay. So all modification of page table entries, whether it is CR3, RPT, whatever it is, it's always a privilege operation. So you trap into VMM, and VMM maintains a shadow page table and so on. Okay. But one advantage of the shadow page table, what I did not say was that, remember, I just made it into a flat. I just said it's a flat page table. Not necessary, right? We already have seen a multi-level page table. And the multi-level page table also. So that means for every translation, I will have to go through multiple levels. And remember, even the guest physical address to host physical address also could be a multi-level page table. Okay? So there is one multi-level page table for under normal circumstances from guest virtual address to guest physical address, another multi-level page table from guest physical address to host physical address. That also could be multi-level page table. Otherwise, you will have to keep the entire mapping. Okay. So therefore, I will have to walk in order to construct or in order to find the guest physical address to host physical address. I have to go through all the multi-level page table, n levels. Correct? And then I have to another n levels, 2 n levels. Okay? But of course, once I do the walk once, hopefully for that particular page, I've already computed this, it's already there in the TLB. And so for all the references within that page, I'll get a very good hit ratio. Otherwise, for every new entry that if there's a TLB miss, in order to construct this to this, I have to walk the host to, remember, all you are given is, let's look at what happens when a TLB miss. Okay? I want to access virtual address 1, virtual page number 1. It is not there in the TLB. It's a TLB miss. So it will come to the VMM. VMM now will have to first walk through the host to physical page table, find the guest physical page, then walk the guest physical page to host physical page, determine this, and then put it into the table. Yeah.
Shouldn't we check shadow page table first before going to the
Huh.
host page table?
If there is already an entry, you're right. If there is already an entry in the shadow page table, then I can do so. Okay. So that is the shadow page table hit. But what if the mapping is not available? Then I have to walk the page table, walk this page table, construct the shadow page table entry. Correct? If the shadow page table entry is there, you are right, then I will just push that entry into the TLB. Otherwise, I have to walk. That's the rule. So now, as I said, this is a pain in the neck in terms of there are all these extra shadow page table data structures. You have to, see, virtualization is not that easy. Concept is interesting, but a lot of hard work has gone into that. Yeah.
What happens to shadow page tables and guest operating page tables upon the operating system switches? When you are switching from one guest OS to another guest OS?
That's fine. Yeah.
Do you store this shadow page table somewhere in your secondary storage?
That's a policy issue. Like swap, do you swap the pages out, the data structures out? That's a policy issue. Okay? Policy versus performance. You want to keep all your, see, there are lots of those kind of issues. One is when you go from one guest OS to guest OS, would you swap out all the metadata of that particular one? That's number one. And second issue is that how much of the metadata you actually want to keep? Do you want it on demand or always static? Okay? Because remember, the shadow page table is just shadow, a copy, correct? It always can be constructed. It can always be constructed because the guest virtual address to guest physical address page tables are already maintained by each guest OS. And I have done, the EMM has done guest physical address to host physical address mapping. Okay? So therefore, I already know that two data structures are there, I just have to combine them. Whether I already pre-computed or on-demand computed, that's another policy issue. So there are two things. One is, should I have the entire shadow page table all the time or only have computed on demand? Remember in the question that you asked, right, on a TLB miss, if I have not pre-computed the shadow page table, then I'll have to walk and then compute. So that's a trade-off between time taken versus memory. Or you could have a pre-computed shadow page table and store it. That also you know. That's a trade-off.
Again, if you want to bring that shadow page table back to the memory, we will still have to write all the entries of this shadow page table to memory, right?
Correct. No, we mean to disk it.
This if you have stored this shadow page table to disk, and again we are coming back to this operating system, so we still have to
Load.
this shadow page table to this memory.
Correct,
So
correct.
there is still right operation being performed on that.
Absolutely, absolutely.
So in either case, it's expensive for
Correct.
operating
So
system.
typically, remember, given the time taken to do an IO versus CPU activity, it's much better from a performance perspective to do on-demand shadow page table construction. Because remember, let's assume as a policy, you decide to retain only 4 shadow page table entries. That's it. After that, I'll recount, right? Like LRU kind of thing. So instead of having all the page table entries, remember, in the shadow page table, for every virtual address, I need the corresponding physical page number, right? I don't want to have, but that are 2 to the power k entries, I could have fixed m entries, right? Whenever I don't have a shadow table miss, I reconstruct. That also I do. So that's all, already some policy issue. So this is the one, but then there is also hardware support in the MMU, right? Remember, instead of just using one pointer, the CR3 register to the starting address of the page table, this is nothing but page table base register. Okay. And then constructing the shadow page table myself, and then the CR3 always points to the shadow page table. But now many of the modern day processors, their MMU is already virtualization aware. Okay. So what does it mean? So instead of the VMM constructing a shadow page table that gives you guest virtual address to host physical address and have only one pointer, which has been reconstructed by walking two different sets of page tables. You can also do what is called as extended page table. What's it called? Extended page table. So what is most modern day memory management unit is capable of taking two pointers. One is CR3 and the other is the extended page table. Okay? So now the MMU don't need to construct a shadow page table. So the MMU takes VMM. Right? So the MMU, the main memory management, is given two pointers. CR3 pointer and an extended pointer that takes care of guest physical address to host physical address. It's given that pointer and this pointer. And then the MMU itself constructs the guest virtual address to host physical address. So this is hardware aware MMU. Okay. But this is, so now the VMM doesn't have to maintain a shadow page table. However, this is a very expensive operation because now, remember, for every TLD, for every reference I need to do, I have to go through, if it's n-level page table. Remember, page table themselves are in memory, correct? I don't have the physical address mapping. So in order to do this, right, I need to find the starting, I know the starting address of the page table, but I need to know the physical address of the page table entry. In order to know that, I need to come to the guest physical address. That means I have to do n memory accesses, correct? And then after I do that, I have to do another n memory accesses to go from here to there. N squared access. Very expensive. Because even for the page table entry, this page table entry, very first entry, is in physical memory. In order to access that, I have to go through levels and then go through another n levels to find that particular physical page table entry. Then from that physical page table entry, I need to calculate virtual address. So that every level I have to go through n cross n or n squared. Alright, give me like 5 minutes, I will wrap up the little bit. One other problem. Okay, let me take a break and I'll finish the remaining. I still have to do IO and page table matching.